Welcome to Ask and Learn.
In this problem, we have a roller coaster starting at a maximum height at rest, and it's going to go through two loops in our points B and C. And we want to find the two heights HA, and HC, and their relation, such that we do not encounter a normal force equal to 0, and we do not encounter a normal force greater than or equal to 4 times the weight of our passenger. So that would correspond to the normal force of 0 would correspond to a feeling of weightlessness, and the normal force of 4 times the weight or greater would be 4 Gs. So sort of two sensations that could be deemed unpleasant, and you would either the feeling of weightlessness or a feeling of too much acceleration could be unpleasant and dangerous. So we want to avoid those cases. So what we'll do for this problem is we'll use the idea of energy, total energy being kinetic and potential energy. So we'll start at the point A and we'll have only potential energy. Point B is at our lowest point, so that will be only kinetic energy. And point C will be a mix of kinetic and potential energy. And so we'll be able to determine velocities at points B and C in relation to that height that we start at, HA. And then we can find a normal force looking at a free body diagram. And at points B and C, we'll be moving in a circle for the loops. So we'll be looking at the centripetal acceleration in those loops to find the normal force. All right, so we'll draw our free body diagrams for points B and C. So those are the limiting cases that we'll want to consider for when the normal force would be either lowest or highest. All right, looking at point B, so we'll have our rider of mass m, and we'll have a downward gravitational force, mg, and we'll have our upward normal force, n sub b. And at point B, our acceleration, our centripetal acceleration, right, will be upwards towards the center of that circle. And then when we look at point C, we have, again, so we have our passenger of mass m, and we have our gravitational force downward and normal force n sub c upward. And in this case, the centripetal acceleration, again, moving into the center of that circle, will be in the opposite direction from point B. And what we know about our total energies and what we can say. So we can say the E total is equal to mgha. So we start at point A at rest. So we have only potential energy, and that's equal to mgha. So our total energy at points B and C is going to be equal to this mgha. And so we'll say energy at B is equal to that mgha, and it's only kinetic energy, right? So this is our lowest point, so we'll consider that our 0 point. So we'll say that's our 1/2 m velocity at point B squared. And so with that, we can deduce what the velocity at point B will be, or we'll just write it. It will be easier to write it in terms of velocity squared. And so VB squared, it will be equal to 2g times that height HA. And same thing at point C. Total energy at point C is equal to mg times height A. And now we have a mix of potential and kinetic energy. So it's going to be equal to mg times height C plus 1/2 mvc squared. And so we can say that our VC squared is equal to 2g times HA minus HC. All right, now we will do, so we'll do our free body diagram for point B. And so we've got our net force is going to be equal to our, we'll have, so acceleration in the upward direction is positive. So we'll say that NB, normal force, minus mg, and that's going to be equal to ma, right? So F net equals ma, and in this case, our a is equal to v squared over r, since we have centripetal acceleration. So it's going to be equal to m vb squared over rb. And then we solve that for our normal force at B and B. And we get that equal to m times g plus 2gha over rb. And we had that given that rb, the radius of the circle at point B, was 15 meters. And so we'll get that equal to mg times 1 plus 2, 1 plus 2 HA over 15. And what we want here, so we want to look at the cases, so our two cases where the normal force is either 0 or greater than or equal to 4 mg. And our normal force at B, we can't be 0, right? Since even if that height A was 0, the normal force would still be equal to mg. So we don't have to worry about that case here. And let's check the other one for when NB is getting to 4 mg. So we want the normal force at B to be less than or equal to 4 mg. And so we have that normal force at B, mg 1 plus 2ha over 15, and we want that less than or equal to 4 mg. And so that means R1 plus 2ha over 15 is less than or equal to 4. And solving that, we get our HA less than or equal to 22.5 meters. Okay, so as long as we make sure our height at point A is less than or equal to 22.5 meters, we won't run into trouble with the upper limit on normal force of 4 Gs. And so now we want to look at our point C and the net force there. And so looking at that, so we have the acceleration is going in the downward direction. So we'll have mg be positive and the normal force be negative for this one. So we'll have mg minus n sub c. So again, equal to ma. And again, we're moving in a circle with centripetal acceleration. So our acceleration is equal to v squared over r. So it will be mvc squared over rc. And so we'll solve that for normal force at C. And we'll get that equal to an m times a g minus 2g and HA minus HC over RC. And then this is using that value for VC squared we found looking at the total energy. And then we can simplify that to mg and times 1 minus HA minus HC over 10, and using our value of RC equal to 20. Okay, so we've got an expression for our normal force at C. And since the height A is greater than or equal to height C, according to our problem, therefore our normal force, the upper limit for normal force C would be if HA and HC were equal, and then we could have a maximum of 1g. So we don't need to worry about the uppercase. So our normal force at C cannot equal to 4mg, but we want to check the case where our normal force at C is equal to 0, and we do not want it to be equal to 0. So we'll get that 1 minus HA minus HC over 10 equal to 0, and that's what we do not want. So HA minus HC should not be equal to 10, right? So we do not want our HC to be equal to HA minus 10. Right. Okay, so those will be our two conditions then. So we want to ensure that HA is less than or equal to 22.5 meters. And we want HC, as long as HC does not equal to HA minus 10 meters. And making sure that we follow those two conditions, we'll keep our normal force within that bound of 0 and 4 Gs that we wanted to ensure.